Hello and welcome to this presentation on issue hiding attribute-based credentials. My name is Stephan Krenn and this is our joint work together with my colleagues Jan Bobolz, Fabian Eidens, Sebastian Ramacher and Samelin. Let me start this talk with a short introduction of attribute-based credential systems. So in an ABC system, we have a user and we have an issuer, and the issuer certifies pieces of personal information for the user. For instance, this information might be the given name, the surname, date of birth, etc. The user stores this credential locally and the issuer can go offline. It's no longer needed in the further interactions. The user can now use this certificate to anonymously authenticate towards different service providers. For instance, when buying a train ticket, the user might be requested to prove that she has a certain age in order to get an age discount. Or when by accessing some online service, the user might need to prove that she has a certain nationality. Now, the core privacy feature of attribute-based credential systems is that the different service providers do not learn any information beyond the information that the user explicitly consents to reveal. In particular, different actions of the same user cannot be linked. So the train provider and the online service in this case could not pool the information to gain a complete profile of our user, unless, of course, the revealed attributes allow for a unique identification of the user. However, in existing ABC systems, the issuer's public key is required for the verification process. So the relying party learns the issuer that certified the user's information. However, this by itself might already be a privacy issue because the issuer might already be sufficient to re-identify a user. Just let me motivate this by two examples. The first example considers a student studying abroad. The student might receive from her university a digital student ID that certifies the name and the current semester. And now when the student wants to buy a train ticket, she might need to prove that she is currently subscribed as a student at some university. Now when the student is abroad, she might already be linkable by simply looking at the issue of the student ID, because there might not be too many students from a specific university studying abroad at a given time. So despite of using ABC systems, the user's actions are fully linkable by simply checking the issuer. Another example is the one of cryptographic attestation of personhood. So we are all used to solving CAPTCHAs every now and then when visiting a website in order to prove that we are human. One of the major cloud services now introduced the idea of using cryptographic attestation of personhood instead of solving CAPTCHAs in order to save time. And the idea there is the following. With a manufacturer that manufactures cryptographic keys, such as UV keys, now when visiting a website, the user is no longer requested to solve a CAPTCHA, but she receives a cryptographic challenge from the website, which is answered by this token after a physical interaction of the user with this token. So basically the user presses a button on the token and the token is going to solve the cryptographic challenge. Now, as stated by this provider, anonymity of a user is guaranteed within a batch of tokens. So when using, for instance, FIDO tokens, the user is anonymous within all FIDO tokens of a specific batch, and batch sizes are at least a few thousand pieces per batch. So the user has reasonable privacy guarantees. However, not everybody is going to use those tokens for authentication, and over time, the amount of active tokens from a given set might decrease, so the user's privacy is negatively affected. And this is exactly where issue hiding attribute-based credential systems could come into the game. So in an issue hiding ABC system, the relying party not only defines the presentation policies, so the attributes that need to be revealed, but it also defines a set of issuers from which it's willing to accept certificates. And the user is now going to prove that she knows a digital certificate from one of those accepted issuers without revealing the precise issuer. So for instance, in our university use case, the user could now prove that she is studying at some university and not at a specific university in order to show that she's eligible for a student discount. So basically we have two security requirements to satisfy: unforgeability and unlinkability. The unforgeability definition is very closely related to traditional ABC systems. So basically we give the adversary the chance to receive as many certificates of his choice from different issuers and to obtain presentation tokens from honest users. Then eventually the adversary will output a set of issuers that should be considered in the presentation policy, and for this policy the adversary should then generate a presentation token. And the adversary now wins if it outputs a valid presentation token which has not been trivially derived from one of the tokens or credentials that the adversary has received from the oracles. The subtle difference in the definition is that we simply need to check that all the issuers that are involved in the winning conditions are honest and have not been controlled by the adversary. Similarly, for unlinkability, the adversary outputs two credentials and attributes of his choice together with the corresponding issuer public keys, and then receives a presentation token for one of those credentials. The adversary now wins if it guesses correctly which credential was used to derive the presentation token, and if there were no trivial ways to distinguish those two credentials. The main difference to previous definitions is that the credentials might have been issued under different issuer keys. Now let's have a look at the construction, how to achieve those security goals. So in the first step, we let the issuer generate a key pair for a digital signature scheme, and in order to issue a credential, the issuer simply signs the attributes of a user. Now, a trivial construction would be the following. The presentation policy simply defines the issuer public keys that are accepted by the verifier, and the user computes an OR proof showing that for one of those issuers that are accepted by the verifier, the user knows a valid credential that satisfies the policy. But of course, the problem with this approach is that the proof size is linear in the number of issuers because of the big OR proof. And the goal of our work was to overcome this limitation. So in our construction, the verifier computes a presentation policy by generating an ephemeral signature key pair and signing the issuer public keys that it is willing to accept. The policy now contains the verification key of this key pair and signatures on all the issuer public keys that the verifier is willing to accept. Now when computing a presentation token, the user computes a zero knowledge proof that shows that the user knows a credential on the revealed attributes that has been issued by an issuer whose public key has been signed by the verifier. The verifier then simply verifies whether the presentation token verifies correctly. And with this, we overcome the efficiency bottleneck from the naive construction, and we achieve proof sizes that are independent of the number of issuers. So what does this mean for a concrete instantiation? In our paper, we give a concrete instantiation based on growth structure preserving signatures. So basically, we use two instances of those signatures in order to assign attributes of a user. An issuer first computes a Peterson hash of those attributes and then computes a growth signature in G1. And the verifier assigns public keys in G2. And for the NISIC, we simply use signal protocols and the future heuristic. In terms of key sizes, this means that our issuer keys consist of one set P element, and the public key of an issuer is simply one element in G2. Our credentials consist of three elements, two in G1 and one in G2. And only the presentation policy is linear in the number of accepted issuers. Finally, as we can see here, the presentation token consists of 7 group elements plus a couple of elements in set P, where L is the number of attributes in the credential. We also did a prototypical implementation of our construction, and this construction achieves our runtimes in the order of a few milliseconds for issuance, presentation, and verification, and the running time for computing presentation policies is about 100 milliseconds for 100 issuers. So that's reasonably efficient. In the main part of our paper, we focused on the generic construction that only supports the main functionalities of ABC systems, so basically issuance and presentation. But of course, the ABC systems found in literature support many more functionalities, which can also be added on top to our scheme. So for instance, if one wants to achieve anonymity revocation and non-frameability, this could be achieved as follows. In the first step, we let the user compute a local key pair and let the issuers sign the user's public key as an additional attribute. So upon presentation, the user follows the same idea as before. So a user shows that she knows a credential certifying her attributes and her public key under one of the issuer keys that were signed by the verifier. And the user additionally shows that she knows the secret key corresponding to the public key and that the public key was encrypted under some opener's public key that can later revoke the anonymity if needed. For revocation, we follow the approach by Nakanishi et al. So in the first step, we embed a revocation handle as an additional attribute into the user's credential. Then in the second step, the revocation authority publishes signed intervals of unrevoked revocation handles. Upon presentation, the user would now show that she knows the revocation handle and that the revocation handle lies within one of those intervals without revealing in which one. However, revealing the revocation authority's public key might lead to the same problem as revealing the issuer's public key, because there might be different revocation authorities for different issuers. So the user cannot directly reveal the public key of the revocation authority to the verifier. And for this reason, we also include the revocation authority's public key as an additional attribute in our construction. And the user then shows that relative to this public key, it knows the signatures on the intervals of unrevoked credentials. Additional features that could be added are, for instance, controlled linkability to ensure that users can, on a fine granular basis, decide under which conditions they are linkable and under which ones they are unlinkable. One question for future research is how to make the size of the presentation policy independent of the number of issuers, because currently presentation policies are linear in the number of issuers. With that, I would like to conclude my talk. Thanks a lot for your attention, and I'm looking forward to meeting you at CANS 2021.